I like that CppCon can dive really deep into the intricacies of the language compared to a more broad overview of computer science in general. I think CppCon is absolutely worth it to attend. If people are having doubts about attending, I think that the best case for attending is being able to see and experience the new advancements in C++ as they're happening.
So hello, I'm Kris. Surprise, surprise. I work for Statistical Securities, and today we'll talk about performance and especially about the measuring, because that's the most important part in my opinion. And why, we'll see, and I'll try to explain why is that so important and why without the reliable measurement it's so difficult to do the optimizations afterwards. And it's especially important in the microbenchmarking world because there is a lot of noise which we have to handle. And all of that is very difficult. And it's become even way more difficult in the last decades or so, because everyone probably is familiar with the Moore's law. The number of total transistors doubles every 2 years. In the beginning, when that started, that was the fact that with that, also the performance increased, the latency of the CPU in a sense, because the smaller the transistors, the faster the frequency was, and we were gaining a lot of boost in the latency of the CPU. That has changed around 2005, where we can reach the limit of the frequency unless we push it a bit further with like heat, and it's like the trade-off is much more difficult here. So instead of that, the CPU is more focusing on throughput right now. So we have more cores, more caches, more data parallelism, and stuff like that. So the number of transistors still is growing, but maybe the purpose of it is a bit different. So all of that matters because nanosecond count, and counts way more than it counted before, because we cannot just wait for the CPU and the frequency to be much faster over 2 years, because that will be more related to the throughput, not to the latency itself. And just to point it out, that the CPU from 2005, like Pentium 4, which is like 4 gigahertz, in comparison to AMD Zen 5 from 2025, will be way, way slower. And nanosecond count for some more than the others. This talk is for people who care more about it. So all of that is because the performance analysis is very difficult. It's a very complex thing, and there is no silver bullet to it. There is no one library, one magic thing which solves everything. So we approach it in stages. So we have this system where we can analyze the networking, TCP, stuff like that, application, when we have the design, data structures, and the microarchitecture, when the most fun is happening with the hardware effects, which we'll focus today on. So you probably heard, always measure is the saying which you can often hear, because if you can't measure it, you can't improve it, right? It's like if, garbage in, garbage out in a sense. So you have to really focus on that. And that's why, in my opinion, it's very important to have the trust to measurement, understanding of it. You have to be able to reproduce them, and so on. So if you're on the system level, firstly, you would do like eBPF, if you're not familiar with that, to tackle the syscalls, I/O, and stuff like that. This is like a great picture of what you can trace in Linux and how to do that. So that's something which you may start with. And there's a lot of aspects here. How does it work is that you have the C kind of code which you compile, and you can run it on the kernel side. When you go to the application level, which we will not focus too much today on, you have options depending whether you have hardware-specific things. So, for example, you can use vTune or AMD UProf and stuff like that. We'll focus more on the perf part because it's more generic and it allows to do a lot of things with it. On the side note, you can do a lot of profiling as well, maybe not a lot, a bit with GDB, which is backed with the reversed call stack by the interprocessor trace. You can do your flame graph and stuff on that. But if you really want to measure something, and hotspotting is not a good idea, and we'll explain that later, but if you really want to measure something, you don't want to measure the startup and the configuration part of it. So perf is great, but you would like to introduce it after the initial step. So the idea here is that we can start it after the startup. That will be a syscall, but if you ever thought how to integrate perf with your C++ code, that's one way to do it. And that will be a syscall, and you will pay for the syscall when you start. Another thing on that level, which is important to do, because you don't want to recompile your application for performance measurement, because that will introduce the bias, which we'll discuss later, and you actually don't want to do that. So X-ray is one of the tools which is great for that, because you can, with basically very little overhead, introduce enabling and disabling profiling. So the way it works, it starts by adding the knobs with a specific number of bytes to the entry and the exit of the function. And then we do the code patching, and we change this knob to the jump. And then we can profile, and we can connect Linux perf this way, and you have one binary, enable disable profiling, profile which you want at any point in time. And that's important because you have to always validate measurements in your end-to-end production-like environment. If you another Clang, you can do something similar. This is one option of the, if you're familiar with the static keys on Linux, that's kind of similar idea. Works with asm_go_to under the hood, and that's how you can do it. So notice here we have this expr boolean variable, which when we set to true, actually doesn't have any state. It changes the code underneath, and then you can start and stop your profiler with the jump, which will be patched at runtime towards your code. So this way you can do a lot of proper, more accurate measurements of the hotspot which you, for example, care about. It's very fascinating how to do that with the multi-thread environment. I mean, the profile equals true. There's one, there's many ways, but there's one very fast way which requires a specific order, which we won't discuss, but if you're interested, grab me after. And also, it's also important to put your jump into the iCache afterwards so that you won't get the miss in the first time. So overall, if you want to check out the tools, you can run this Docker file and see all of them. But what I want to point out is that the hotspotting, which we have been doing here, doesn't mean the speed up. You can overall speed up. You can, optimize some function, and you won't get overall speed up of your application or something. It depends how you approach it and what you will do with it. But that's the overall point which I'm trying to make here. Also, that you don't have bottlenecks doesn't mean you're fastest as well. So really depends what you care about. Finally, I just wanted to point out COS, which is a great profiling tool for if you have multi-threaded application. The way it works, it eliminates, artificially slows down and speed up part of your component, and then measure the overall performance and how that impacts it. If you haven't tried it, you should. So all of that, I'm going a bit fast in the beginning because that's kind of very basic stuff which you can easily find. Right now we'll get to the more interesting part. So we will get to this microarchitecture where, finally we go to our microbenchmarking part. And why you want to do microbenchmarking? Because, well, the iteration speed is if you have to run on the production machine or something like that, that's slow, iterations are slow. And all of that makes it a difficult process, like corner cases, data distribution, coverage, very, very hard to do it in the production line environment. So we want to optimize it with microbenchmarking. And that, the idea is here that we have a piece of code and we just measure it. It's very important how we measure it, though, and what we'll get out of it. So for example, let's take a look into a FizzBuzz function, a simple one, which I've chosen for a reason, but we'll see later. And if you try to understand what's the performance of it, we can use libraries for benchmarking, which do measure something. And it's really hard to say if you get 42 nanoseconds, whether that's good, or what does actually means, and what conditions. The same if it's faster than the other version. All of that is really dependent, and the complexity behind the performance measurement is really hard, and the noise which ratio in the benchmarking also has to be taken into account. So the ground jewel of this talk, let's talk about the microbenchmarking pitfalls. I poetically named a few of them. There's a lot of them, but that's the one which I believe it's worth focusing on. So we have the noise, which is relatively simple to deal with. We have the bias, which is the hardest. That will be the hardware effect. The faith, where we have the numbers and just trust them. The chaos, how we optimize it. And the illusion that we have our micro benchmarks, everything is 50 times faster, or a few thousand times faster, and when we apply it to the production, it is slower, right? I don't know whether anyone has seen that before. Right, so for the record, everyone will see it soon. But okay, so just a disclaimer, because right now we'll go into more details and more hardcore stuff, so hopefully at least some of you will enjoy that. So we'll focus here on x86 because microbenchmarking on the architecture is really depending on the architecture. But some of these things, most of the things apply across. We'll also focus on Linux because that's the easiest one to deal with if it comes to the performance. And you will see a lot of shortcuts here, which we'll use afterwards. So I just tried to give you the names. We can follow up with RIII, I guess. It sounds like it would fit here. So you can see that CPU vendors have a lot of shortcuts as well for the performance monitoring unit, which allows us to get the better understanding of what we're actually dealing with. And I wanted to point out that the CPUs are a bit like system languages. So you can use C++, Rust to make things fast, but how easily you can tweak and verify it really matters. So for example, Intel is really good with providing the tooling if it comes to the understanding the performance. And I specifically will say here about the Intel processor trace, which we'll use extensively here because it's great for microbenchmarking. That's also available on Apple M4, but it's much harder to get to it from that perspective. So we'll leverage this library. It's not that important, but it's just easier to illustrate because I've been working on it. So we'll use Linux perf, kernel API, which is the perf event open. We'll use IPT, which is the Intel library to get the Intel processor trace decoding. We'll use LLVM MCA, so LLVM dev, we'll use that in C++. And for plotting, we'll use GNU-plot and Sixel, which will allow us to plot on the terminal, normal terminal, as well as TTY if you move to the hardware machine after. So let's start with the noise. So the noise starts when we hit the main, or even earlier when we have a global variable or something. And the main reason for it in that environment is that we have OS behind it. So that's a map of Linux. And you can see here there's a lot of moving pieces, not just one. It's not a simple thing. If you can put a number on it, be my guest, but I would claim it's difficult. It's a really complex thing. That's the theme of this talk is. But you can do a few things. The noise which you care about will depend on your setup and your application. But some of the common things which we want to avoid is, for example, the kernel mode tasks isolation, so that will just pin one of the CPUs to a specific that the kernel won't switch it, which is important in microbenchmarking. We can do a lot of disabling of the features. You can use PyPerf, system tune, if you can be asked, figure out what you really want to disable, but I would encourage you to do that. And then we have priorities and affinities, which you have to set up for having less noise, unless you run with the noise in the production run. That will be probably difficult to optimize. But one of the coolest idea, which I got actually from Ignace, who is here, is to use UEFI. And this is a way you can avoid the noise altogether. So if you really care about the nanoseconds or cycles, you can get and avoid the kernel altogether, go to the UEFI, ring 0. All the privileges are yours. You can also disable CPU features. And I encourage you to do this experiment once in your lifetime to appreciate how CPUs from 2025 are better than 2005. If you disable cache or branch prediction and run some code, you'll definitely see and appreciate it more. But it's a very great tool to go really low level if you care about it. The other thing which I believe is really important when you start microbenchmarking, and we'll get into harder stuff later on, is to have the sanity checks, right? So we want to print, for example, where we're running, how we're running, and just check that we optimize, don't profile, debug builds. You won't get much performance out of that. One thing which I wanted to point out here is that I would advise to log CPU ID. So you can have this family, model, and step-in, which gives you the ability to quickly log it online. And unless you run on specific hardware, you will get all the information which you can print otherwise either way. So just a side note, since we're using modules here, because it's C++ 20+, one thing which I find very interesting with modules, and I think that's the main premise of them, is the fact that you can have compile time testing in your module, which you expose or not, or actually do not expose, like your static assets and context per compile time test. And then it will be compiled once when you compile your module, and all your compile time testing will be already there. So I believe that's very important to do when you expose a library, because otherwise you will deal with people just not running the tests either way. So that will verify, and this specific case is very important because it's your CPU, hardware, and compiler specific. But the other thing which we want to do before we start dealing with the noise and microbenchmarking is to do some runtime checks. So let's do self-testing. On the left, you'll see if the machine is not tuned very well, meaning we didn't do the noise reduction of some sort, we'll get a lot of noise. And if we not care about that noise because it's not part of our experiments, and that will influence the benchmarking way more than they should, and our conclusions will be as the noise. On the right side, you'll see that if you optimize it better, you will have better results in the end. But what we can do as well, since we have LLVM in that case and other things, we can verify the measure versus documented thing. So this will be an example of the startup of like a perf, in which we'll verify that the basic instructions, latencies in that case, have the same values as the MCA providing from the scheduling model, which is used by LLVM for optimizations. So if they match in, notice that the diff is really slow. Probably everyone knows why. Well, not why, but that it is. So avoid it. But you will see that it matches, meaning our framework is tuned for performance, and you can check those numbers if you want in like UOPS tables and Agner fog instruction tables as well. One thing which I wanted to point out, if you go to the microbenchmarking on the cycles level, there are a few tools which you can leverage, like LLVM has one for day measurements. They verify whether the scheduling model which they have in the LLVM matches the reality for the platform, and so on. So okay, so this is just the noise. Noise is kind of simple to deal with. Let's talk about something more difficult to deal with, actually the bias. So there'll be a lot of things here, but the goal is to have reproducible results, which we can apply then to the production code and get actually reliable things, results as well, meaning they correlate to our benchmarking. And if you haven't read those papers, I'll just link them here. They're really great, especially the producing your own data, the first one. It shows how environment variable in Linux increases changes the alignment of the stack, and in their case, they measured it as a 30 to 300% slowdown of the application. So, but that was back in the day. It's a bit better right now, but the problem still exists, which we have to encounter for, because you don't want to have measurements different when you run as a full versus bar, right? Makes no sense. So why all of that is so complex? Probably you've seen the Linux, well, you've seen it, you've been here, the Linux map. There's also the CPU kind of chart here, which is also complex. It is actually even way more complex under the hood. And that's what we run our instructions, which we don't even run instructions like on CPU, we run microoperations. But all of that points out to the complexity to what is happening under the hood. All of that was much easier back in the day. It's much harder these days, and we cannot just ignore that anymore. So just a few words about the measurements. They are not independent, and they are not normally distributed. And it's really hard to get to the normal distribution to do the statistics on it. So we have to do a lot of runs, and I advise you to do that so that you have samples and iterations if you have to get somewhere closer to the measurements, which are like a normal distribution, so that you can do some statistics on it. Because if you take mean and you don't have a normal distribution, that won't be really valuable for you. And we would like to answer, is this thing faster or slower by some percentage with a given confidence? And there are different clocks which you have to use. We will use timestamps counter because it's the thing which we, allows us to measure the low part of the cycles. But it's often used a high resolution clock from STD chrono, which is the worst idea, and because well, that's one, it tried to be deprecated. Two, it's an alias to system clock or steady clock. Steady clock is fine, but system clock is not fine. You might get, it's like, it may change it's a calendar clock, so it is allowing, to change the date so you can get negative numbers there. So don't do it. So let's take a look into the normal distribution, which we don't usually have. So most of the microbenchmarking will have skewed distributions or binormal distribution or whatever distribution, but really hard to get to the normal distribution overall. So if you plot it, which I always advise you to do, if you don't have the normal distribution, take some other statistics which you can then overall reason about. If you can't, just don't take the mean. Mean will not give much value here. So I was pointing out about the noise. Right now I'm talking about the bias, which is the most important because of the hardware effect, which we'll take a look in a second. All that is use case specific, but if you see the bars like here, and you don't see these error bars, which shows the variability, it's really hard. It means that it was probably one measurement or it's a mean or something, which then is really hard to reason whether it's faster or slower, because the first one might be sometimes slower or sometimes faster. So if you really care about, you have to show all of that and not just assume it will be better or worse. So let's get to the latency versus throughput. So most benchmarking will just do the throughput, and we'll discuss why in a second. But there are two different measurements and two different metrics as well. So latency, it's time to takes for a single operation to complete, versus throughput, which is the total time, total number of operations completed in a given amount of time, usually a second. So that's very important to distinction when you actually measure it, because when you do latency, you can do it by start, call a function stop, but you won't get much resolution out of it often. So it's valuable in some cases, not all of the cases. If you do a loop, you actually have to introduce data dependency between the run in order to get it sequential. Because, otherwise and sometimes we need to do memory fence as well if you have a write to get it sequential. We have to subtract the overload afterwards. But with latency, that's very simple. Throughput, on the other hand, is like if you have a loop, what is happening with this question mark here is the fact that CPU doesn't wait for us. It's like, because we have a closing bracket on the for, I'll wait. No, CPU goes ahead of you. And that's kind of the key to performance as well. Like performance is not gain at the current time, it's gain in the future. Like if CPU is far away in the future, you're fast. Otherwise, you probably won't. So the throughput, you have different policies to measure the throughput. Like here's the sequential policy when you just have 4, but you can go into different approaches as well. I advise you also to read the low overhead tool paper, which is used for the nanobench, probably not the nanobench you've heard about, the nanobench which is used by UEFI, and they show how they measure the latency, for example, by unrolling twice as much and then unrolling just once and subtracting that. A very interesting read if you're into that. Okay, so then the latency itself as a metric is also different than the and throughput versus the measurement, right? So latency will be the nanoseconds per operation, which is the time. The throughput will be the operations per second. You can get the throughput by gigabytes per second. You can get inverse throughput, which is also the measure of the measurement throughput, but the metric is inverse throughput, which is the same as the latency in that case, but from the different measurement. So you have to be aware of that. And I just love this picture, so I just put it on to show the difference between latency and throughput. If you're more latency related, you often will go to FPGA or ASIC or something like that, and that will be for latency. For throughput, usually you would go to a GPU. So, and in between is the CPU, which is what we're focusing today. But I just really like this picture. Okay, so right now we'll focus on the hardware effects of microbenchmarking and the code in general, which affects everyone. And if you're not taking care into consideration that it will affect you, you will miss out. So for example, unused function may change your performance dramatically because of the code layout. It's not even used, it's just a function there. You compile it in, and that will change your performance characteristic. It will change the code layout. You may be on the cache boundaries and stuff like that. Stack, how it will be aligned, will change your performance. Memory access, obviously. Branch prediction, the most important. Data layout, all of that will change your performance characteristics of a microbenchmark. So if you have a microbenchmark and you just took the default or whatever, it's really hard to take it and apply it to your code in production, where it's like a different layout, different thing, and doesn't really work well. It also doesn't say that you should remove dead code, because maybe the dead code makes you fast. Just kidding. So let's talk about branch prediction and cache is the most important, so we'll focus on that a bit. So modern branch prediction can learn like 10,000 10 branches or something like that. I think that's on Apple. And for the record, like the static branch predictor, if you have no history, backwards branches will be taken, forward will be not taken. So that's for the loops, but just in case if anyone was wondering how does it work. So this thing is really complex. I really advise you to watch some hardware talks, how does work under the hood. I have some resources afterwards. But what is important here, that when we have our loop and we would measure with the same parameters, well, the branch prediction is way smarter than we are, and we will have the history, 10,000 elements, whatever, per IP, which is the instruction pointer, so, and there's like global and a lot of things there. So we have to change that. We have to have a kind of distribution of the inputs. So let's take a look into, and that will be use case specific. So if we bench, for example, this fizzbuzz, we pass compile time constant, and we have like an auto parameter. That will be elided, or maybe you familiar with like optimized, which is the wrong word, but anyway. So that will be a different behavior than if you pass free or constantly, and totally different if you try to treat the branch predictor, but by giving like the sequence, range, or unpredictable, which is like uniform distribution, or a choice, which have certain probabilities. And also, it's really important to remember that if you have a heap, like malloc and all of that is really smart, you have to pollute heap when you push into those things in order not to have unrealistic scenarios. So if you run it, we'll get a lot of numbers, which I already knew it would be really hard to see. So let's move to the charts. That's why you want to plot things, because plotting is much easier to reason about. So you can see here that the error bars are small, meaning that we were able to reproduce that to a certain degree without the noise. So bar will show us, lower is better, but what is kind of important here is the fact that the range, which is the green one, the third from the right, is if you have the iteration for loop and you just put I of the iteration into your benchmark, which is often done. So we do for and we pass the iteration into the loop. We change the parameters, we change the data, be good. If you have branches in our code, that will be predicted most likely. I put here 1 million. So you can see the difference in the profile. Also, what is kind of interesting, that the uniform distribution, which is hardly ever in the real world, but it's much slower. But even slower is if you have unpredictable worst cases often, because we have to do a lot more. So something to, like, if anything, just do that for the microbenchmarking, because that will change the results very much. So the other thing which we want to focus on when we microbenchmark is to show like histograms, so that we can see the data distribution, because they will be skewed, so that will give us better understanding what statistics to use. There are different ones like boxes. We can show our outliers and the tendency of central tendency and variability. But I wanted to show the, in my opinion, most important and not used that often, empirical cumulative distribution function, because that shows everything. There no smoothing, nothing like no buckets, nothing like that. All the points contribute to the results. So you can easily compare all the measurements, all the samples which you've done, which you had to do either way, to see how that affects the performance. So really encourage to use those. And they show cumulative data proportion. And just a side note, because all of that was on the terminal, so that's not UI or anything, that's the terminal, and the terminal emulator. If you're interested, Sixel, which is supported by all the terminals, like Windows, Mac, is just a format which you print, and when console, the terminal will show a pixel and all of that. So this is pretty cool, but often when you move to the your production machine or something like that, you want to use like TTY, which you can do as well. That's the same chart plot, just where it's looking. And also, if you're familiar with Jupyter Notebook, that's also a good choice to do the analysis. Okay, so let's take a look into a second one, which is the code layout. So as I pointed out, code layout will affect the performance of everything. So you compile, you change anything. Therefore, I was saying that if you change the profiling and you compile that in, that will change your profiling performance result. So be aware of that. So what we can do here, from like application level perspective, we can enable address space layout randomization, but that's fixed per run, and that's a security feature. But we can use it for the fact that the heap will be randomized and stack will be randomized. For the code itself, there is like Clang and Molt support layout randomization, where we can shuffle functions around and see how that affects it. That will be per run, though, so you would have to recompile, and go about it many times. There is this, not maintained anymore, but a great tool, Stabilizer, which was using LLVM under the hood to randomize those things at runtime every half a second. So that was pretty cool as well. However, you have to have a lot of long-running things to get the normal distribution out of the results, and how that affects the branching and other things, it's also difficult. So we can do, from benchmarking perspective, we have this function 1, and we can do different benchmarks. We put some config on it, and we can do the different distributions of the values. So, for example, we can align the loop, because if you do not align basic blocks, compiler will choose the alignment for you, which might be not what it will choose when you in different contexts, like your app context. For loop boundary, that also depends how big your loop is, whether it will affect or not the stack size, the stack alignment, the function alignment. The function alignment is 16 by design, for example, with all the compilers right now. And you have to run in the new process as well to get a bit ahead of yourself. So you have to do that. Then we'll get to the cache, and that's even harder to do. I really encourage you to see what the hardware is. So LS Topo is on Linux, where you can just see that L3 is shared in most cases. So, and how many NUMA nodes you have, and stuff like that. But that allows you to then, for example, if you have L3 being shared between different cores, you can trash it from a different core, you use false sharing to benchmarking. You should read, by the way, the paper described here if you haven't. But what I've been experimenting with and works pretty well for me, and we'll discuss how to do it afterwards. So what I've been doing something like that. So run a distributed already, as we pointed out, the branch prediction and stuff, function to collect the executed branches, addresses, instructions on the instruction pointer basis. Then we do our loops, and we actually set up the branch prediction and flush the cache based on our profiling results. So we have the results, we know there's a lookup table, that's the addresses, and then we have the distribution of what do we want to measure. We want to measure if it's 10% full, 50%, 70%, and the same with the branch prediction, because it's so hard to get to all the branches outside, so you have to go from under the hood. This is difficult, and it's really hacky, but it works. If you have L3 open it up, you can do it from a different core, so know your hardware. And then you cannot do the loop here. You may sometimes go with unrolling, because if you do the loop, the cache and the branch prediction is very fast to learn, and you will lose all of the setup which you made. And you have to use something like fast things to measure, like the cycles. So all of that, I don't want to scare you. There's a lot of more of it, and you can go higher or lower. You can go into execution ports. That will also affect which ALU, for example, will be chosen. If you have a code surrounding it and it's already used, and in microbenchmarking wasn't, that would be a different result. So there's a lot of things here which one has to consider in order to actually map the results with certain probability to the code. As I put out, it's not easy, and there's no silver bullet, just a lot of work. But there's a lot of gratitude when you make it right. So the faith is something which we'll look into right now, meaning, you have the timing, like we did, the bias, we did the noise, and right now we get the timing, we feel good about ourselves because this is faster, this is slower, we go and ship it. Well, now, it's like without understanding why, it's not really that valuable because you will miss some bias either way. So you have to go through that. And a lot of these tools, because Matt is here, so you can check out on the Godbolt Compiler Explorer, there's a shout out. But I wanted to point out that sometimes when you do benchmark, you profile with the filter, just this one benchmark, right? So will that affect your results? Will that have the bias? As I pointed out, yes, it will. It will potentially change your results. So that will be related to, for example, the environment variables and the stack alignment and size. So be aware of that. So what we can do, we have to do some profiling, and for that we have this ability with profilers. We can count, and in the C++ world, we want to count syscall free. So here will be, if you want cycles, instructions, and like timestamp counter, we'll do that with the instructions provided by the CPU. So RDPMC and RDTSC is something we want to use to be syscall free to have better measurements. So to be in a cycles world. We can do sampling as well. We have to have some hardware support for that. That will give us the results per instruction pointer. And then we can more reason about it with analysis, which I will show in a second. But you have to be really aware that sometimes you have to do a lot of measurements, especially when you do analysis, because there's this multiplexing, which happens because there is just likely 8 hardware counters which you can use in the CPU. And tracing, my favorite for the microbenchmarking, we just we just record the instructions being executed and then reason about it. So that's something which you can also get the cycles, and the accuracy of the cycles will depend on your hardware, but you want to get as close as possible to it. So then we have the profiler. We do start, stop. Here, like notice this prevent elision. It's the same, like, in my opinion, it's the right way for naming do not optimize, which is so confusing because a lot of folks sometimes think that it's, I'll prevent optimization. No, it's prevent elision, compiler elision. So we log, we get some cool numbers. We good? Well, no. We have to go a bit further. That's where we go to the MCA, for example, when we have to disassemble those things. And that's something which we can leverage LLVM for. So here, I pointed out in the beginning the scheduling model that you can find it in the LLVM project and see all these numbers which they have, verify whether they're correct for your setup. So here, we have to introduce, because we're in C++, we don't have size of the function. We have to do kind of some magic. We can do labels. I put it out as go-to. We'll leverage that again because that prevents reordering, and we can get the labels of the code. It doesn't emit an instruction. It prohibits some optimization sometimes, but doesn't emit an instruction, so the code is the same under the hood. And for MCA, we don't have to run it. We can just take the pointer and get the region. That's probably small, but that's not the point here. The point is that we can do a lot of analysis based on that. So here we'll focus on the annotate, which is the per instruction pointer. So what we can do, sometimes some may think that less assembly instruction is better. Well, that doesn't mean much. Assembly instructions have different latencies, and they execute a different number of UOPs, they have different throughput. All of that we can get out of the MCA for your machine if you have a good scheduling model, which you can verify. And also, maybe not that important, but I like to point it out that like CISC versus RISC, like it's not about the instruction number because all of them have tons of instructions. It's more about the encoding part, and the coding ARM will have the static one, and x86 has a variable length. Neither doesn't mean it's faster or slower, it's just different. We can see the resource pressure. So for example, there's a lot of execution ports on the compiler, which you can see in this diagram, and there's also a lot of LUs, and you want to see which ports are being assigned and used in your code to understand why. And you can do a lot of more things. For example, you have the code like that, and you can do this throughput simulation where you have the assembly of this code, and you loop multiple times through it, and you will see the execution. So the timeline here, which we really want to avoid the equals, you can read about the MCE timeline. That's like how per each cycle your CPU is being executed. One thing that I wanted to point out is the disassembly, which you can easily get out of Compiler Explorer, and the tracing, which you can't at the moment because you have to run your code with the specific values. So here will be the begin-end region, and we'll have 5 instructions and some timeline. And on the right side, we have the trace, which, depending on the input parameters for this function, will have different results and different instructions being executed. What is pretty cool here that we can, grab for our code what has been executed, pipe it to timeline, and see how on the CPU to certain degree based on the MCA scheduling model, and that gives you a lot of better understanding why and how things are happening on the low-level side. So then we apply that to our benchmarking for the latency in that case. And if we do the region, we'll see like we run FizzBuzz with 15, 5, and unpredictable, which means like we randomize the input. If you get the assembly, that will be the same. But if you get the trace, meaning what instructions have been executed, there's a different story here being told. So 15, because like if you look at the FizzBuzz, that's like the first part where we can, don't care about the rest because we return. So this is different, right? What is also cool, we can do comparison of the timeline, and if you look into that a long time, you will see quite a lot out of a diagram like that, so, which I encourage. And you can do a lot of other things, like you can see where the loads were coming from and the branch prediction. So like 15 didn't miss anything, like FizzBuzz 15, the same as, and this is like based on frequency as well. And the 5 doesn't miss anything, right? And the unpredictable will miss because we tricked branch prediction. And you can do flow charts, flow graphs as well to see it better, or flame graphs, and you can use LBR to get them out. And then, one important thing about the flame graphs is that they do not have time in it, there's just occurrences. So be aware of that. Okay, so we'll have to go through the chaos right now, which is important part when we done the timing, we have the timing. When we did the analysis, so we more confident into why, but what we go about it, how we optimize all those things. And random walk will give us into like local minimum and ideas and 20 years of experience to know what to do. Modern CPUs are usually bottlenecked by, if you supply all the instructions, well, that would be really good, but likely unlikely. So what we can do? We can reduce overall instruction count, increase the per cycle, instruction per cycle or UOPS per cycle, and additionally, we can apply top-down microarchitecture analysis where we don't have to think about it that much, meaning we don't have to come with the hypothesis. What if I will change that, and how will that, this is random. This won't lead you into the right spot often. But you'll never know. And also, it's like if you try to optimize for instruction per cycle, like UOPS per cycle especially, you know when to stop, because you will never hit more than the dispatch width, which you can take from the scheduling model. For other, there'll be 6. If you have UOPS per cycle max being 6, well, ain't gonna be faster than that. So let's take a look into the top-down microarchitecture analysis. So we have to have a goal. So that's from Intel. Intel says, based on type of application you are, that's your rough numbers which you're aiming for. You can obviously say, design it yourself. But the idea is here that we cover the whole CPU in this diagram and just go around it with the analysis. So first, there's first level, whether we are retiring instructions or we have misses or we front-end or back-end bound. We do that, then we do the second round. So for example, we are back-end bound. We see that it's either core bound or memory bound, and we have counters for that. And then we go deeper. Let's say we were memory bound, and it's like L2 bound. So we know what to optimize and what will have an effect of the optimization. But all of that makes no sense and won't give you the results if you have the bias or the noise. So you have to have all of that in order to actually reproduce the results in the end. So that's how we can do that. Not that important. But what we can see here, just to point out that if you have this sequence or something which is predictable very well, we won't be branch prediction bound, which is bad because we are, but that won't be shown. So you can use this analysis method, which is structured, gives you sanity in your work, but you have to have the bias and the noise removed first. And then, if you have that, then it's easy. Like all of that is documented. If you have retiring, what you can do, what to apply, then you can learn, I'll learn SIMD. If you have bad speculation, I can, watch feeder talks and go branchless. Or if you're front-end bound, you can, go TMP, whatever. You get the gist. So finally, we've done all of that. So we have we reduce the noise, we get the timing, we understand why, we did it properly from the chaos perspective. So we have the understanding, and then we have to also apply measures to always ensure that it will go through to the production. So for example, we have to there's no point if you fast and you wrong. So for example, if you sort, in that case, you would like to verify that all of that is being sorted after you sort, right? And that's very difficult to do outside of the benchmark because you don't have this call anymore. So we can do that in some benchmarking way, TMP way, but the thing is that you won't affect the benchmarking, so you'll get that out. And my favorite out of all of that is the testing. If you have all this tooling, we can actually apply, the testing which will give us the answers for what we potentially care about. So we can disassemble, we can trace, we can analyze, and we'll leverage the tools which we shown here. Not that important how, you can ask me after. So for example, we can test the disassembly of a fizzbuzz function that it has 19 instructions. And what these instructions are. If you really care about something being the same, you can do that. It's not ideal way of stress testing things, but it's sometimes, especially if you have like something with logs or something like that, you might want to verify the order of things that it's actually happening the way you want it. You can trace, as I pointed out, it's a different thing than disassembly. So if you're relying a fizzbuzz with 15, we'll get 7 instructions. So we can verify that and verify whether everything makes sense in the end and just test it. And my favorite is like, what if we have one function and the other function, and we verify that C++ gives us the optimized way. So we can compare the disassemblies, or we can compile the traces for the specific arguments. And in that case, we have UB here, and that will be optimized to basically return true. But then you can imagine what you can do with that. It's a lot of potential to understand and ensure that in the future it will be what you assumed it will be, and if it's not, well, it will fail, which is also important to know. And my favorite by far is to analyze. So as I pointed out, we have this timeline, so we can, run, and that will be from there's a lot of aspects here. So we run the fizzbuzz with argument 15, we record instructions of this run. There will be 7 instructions, and then we can verify how cycle per cycle things have been dispatched on the lower level. So I found it extremely useful and cool to do. And then, which is the most important part out of all of that is, so we did all this work. We tried to reduce the noise, bias, our measurements as statistically sane, and we ran it with the profile, which doesn't change the bias again, and our benchmarks are slower, but the application is faster. What do we do? What do we do in that case? Ship it? It's faster, right? Well, no, meaning we've done something wrong. The correlation is really important. That's why, this car is F1 car corresponding to the wind tunnel. That, if you don't have a correlation between the wind tunnel and the racetrack, well, your optimization makes no sense after that. If you do not correlate your microbenchmarking, there's no that much value in them for that specific reason if you care about applying them for the future optimizations. So what do? You go back, verify why. Maybe it was the noise, maybe it was the bias. There's a lot of biases which you couldn't maybe seen, and then you try to correlate it. And if it correlates, then you apply it. So to sum up, because we're running out of time, always measure, but just measuring, for loop and divide by number of iterations likely won't get you far. Better than nothing, but maybe not. And we want to avoid microbenchmarking pitfalls. So there's a noise, so we want to tune it. There's a bias. They have to have the modeling, how to approach it. The CPUs are so complex, as well as the OS, that it's difficult. It's not an easy task. We have to have the faith after that what we measured makes sense and why. Because if you measure something and you don't understand why, like that doesn't make that much value. And ideally, we avoid this chaotic, I will optimize that, I will optimize that. Let's just learn the hardware, approach it in the structured way, and go about it. And then validate, like the most important part of that. You've done all of that, we validate in the end, and then it correlates, it improves the performance in the production. We have the framework which we can deal with, experiment quickly, fast iteration. All of that is then great. Mandatory slides. Well, as I pointed out, some care more about nanoseconds than others. HFTs usually care more. And here, I just wanted to put out the further reading, because I just scratched the surface. There's like so much more. I just pointed out a few things which, in my opinion, are important, the most common things, but there's way more. So I really encourage you to read the manuals. They're long, but if you read in C++ standard, it's not much different, it's actually better to read. And I collected all the resources on this website if you want to take a look. And with that, thank you. If